All right, dude, we are live. What's up, guys? This is Dem Keys, and we are having one of those rare days where I'm able to stream twice a day. So we are doing the second stream of the day, which, to be honest, isn't really the second stream because we might as well call this the first stream because the first stream that we did, the actual first stream that we did, which was a couple hours ago. Actually, how long ago was it? I think it was about 5 hours, five and a half, I guess, 5 hours ago. Um, we tried to do we tried to do one stream. That was the first stream of the day, and that stream only lasted like 15 minutes before OBS crashed, and I wasn't able to started back up in time before the disconnect protection time ran out, and because of that, uh, the stream ended. And at that point, I was like, you know what? I was planning on doing only like a, I don't know, 45-minute stream or something, and 15 minutes have already passed. So yeah, I might as well just end the stream here. But luckily, now, 6 hours later, I discovered that another window opened up for me to stream. Hopefully, I might be able to stream for 3 hours. I'm hoping to be able to stream for 3 hours, but usually my voice doesn't last that long. Maybe keep I'll try to keep in mind that I have to speak low, so that it can last a little bit longer. Okay, so let's let's sort of restart from the beginning. Let me also talk about the stuff that I talked about in that other 15-minute stream. So basically, today we're gonna be doing, because I'm kind of in the same situation right now as I was 5 hours ago, where I was like, I'm not sure what I want to stream today because I already have a couple of things that I've been doing, um, which most of them were like off-stream things. So I wouldn't be doing them on stream necessarily. And because of that, because I was already in that mindset of doing those things, I didn't want to switch to doing the deep learning research. The other stuff was also deep learning research, and uh, actually a bunch of other things as well, electronics research and some other Git related research. There was a bunch of different research, but what we study on stream, specifically what we've been studying, which was how feed-forward neural networks understand their data, understand the input. That specific thing, I didn't want to switch to that suddenly because I was already in the mindset of doing those other things. So I was like, okay, what can I do on stream, which would still be, research like. And then I remembered that I'd asked Google Gemini a question about, it was sort of a where do we go from here kind of question. I'll get into that. Before that, I also wanted to talk about, and I mentioned this in the previous stream, the 15-minute stream. There's a couple of Git related things that I need to. Actually, I think I wrote those things down. Did I? Or did the thing crash before that? Oh, yeah, here it is. So, Git related stuff specifically. Fortunately, I've learned the basics of Git, um, and I have a pretty decent understanding of how Git works. I've looked into branches or branching. I've looked into branches, and I've also created branches and merged branches. Just basic branching operations I've done, but I wanna properly understand branching and how to solve possible issues that could occur. One issue that I've pretty often faced with branching was merge conflicts, and I've also faced this issue with when trying to push changes from like a working copy of the repo to the main copy. So trying to push the changes to the repo, basically. Or, well, they're both repos technically. No, you know what? No, we'll call the main thing the repo. So when trying to push changes to the repo, um, sometimes I would end up with certain errors that I didn't really know how to solve them, and a lot of times these errors would occur when I was dealing with Unity projects, because Unity projects, they aren't like, two, three, four file projects. They often have like hundreds of files and lots of different directories for different purposes and stuff. Some of them you can just ignore when you're working with the Git repos. So it would have been good to know that back then, but I didn't know that back then. But yeah, anyways, so there's four things I think that I need to look into. One is branching, which, like I said, I've already learned like the basics of it, but I kind of want to dive deeper into that. Then working with remotes, they have a whole section on working with remotes. Before working with remotes, I believe the cloning, pulling and pushing, all three of them, or I should say, I believe clone, pull, and push all come under working with remotes. But and by the way, I've also already explored working with remotes to a certain extent. I haven't like finished the section, but before I start working with remotes, I also want to learn about the Git protocol, specifically the Git protocol, and setting up a no auth um, let's say local server, local Git server. There was a fourth thing that I can't remember right now. There was something. There was a fourth thing as well. But yeah, for the time being, until I remember that fourth thing, these are the three things that these are the three Git related things that I want to do research on. And after I've done this, I'm going to be able to start working on those projects that I wanted to work on. Because there's been a bunch of projects that I wanted to work on that I put on hold. Some that I wanted to continue working on, like my VTuber app, for example. So there's been a bunch of different projects that I wanted to work on, and in this case, wanted to continue working on, but I kind of had to put them on hold because I wanted to move a bunch of them to Linux, to my Linux machine, because I installed Unity on the Linux machine and it seems to be doing pretty well. And I want to continue working on projects there, and I also want to start projects there because it just seems to work out so much better than doing it on my Windows machine. So what was I saying? Yeah, once I've you know gotten the knowledge that I need, because I already know the basics, but I feel like these specific topics are necessary if I want to set up the infrastructure to do Git stuff. Because the thing is, I want to set it up in such a way that um, one of the machines is going to have a bunch of the repos, and then I can like clone the repos from that machine and start working on them on a different machine, so that way there's like a fixed backup kind of thing. And the great thing about Git is that anytime there's a clone, that's kind of its own backup as well. So if the main repo, uh, if the hard drive dies, for example, for whatever reason, or if the data is just lost for whatever reason, the main repo is kind of, it's there. Like we have the we have a full working copy of that main repo, so we can just set up a new repo out of that. So that is Git related stuff. After that, there's also ESP32 and just in general electronics stuff that I want to do on stream. There's a bunch of research that I have to do relating to analog electronics before I start doing the analog electronics. I say analog electronics as if I'm going to be doing some very complex stuff. No, it's going to be simple stuff, but it's going to be stuff that I've had doubts about for a while. Stuff like it. Okay, so in terms of calculating, how much current is going to be across an LED or within a circuit when you introduce a certain resistor. Those are simple calculations because there's very few components involved. But once you start connecting more and more components in there, more and more discrete components in there, be it whatever, LEDs or resistors, capacitors, transistors, diodes, whatever, the more components you start adding in there, the more complex the circuit becomes. And then there's, of course, also the way that you're wiring it, whether it's in series or parallel. And pretty soon it becomes important for you to be able to analyze these circuits. And I guess the term for it is solving the circuit. I don't know. I've never really understood that part. But yeah, circuit analysis becomes, or being able to analyze circuit analysis becomes very important. And yeah, that's where it gets a little bit complicated for me. That's where I've had trouble with more complex circuits, not the simpler stuff. Once you have like a whole bunch of different branches going out, it becomes, I need to learn how to analyze those circuits properly so I can set up those kinds of circuits. I also want to learn how to do calculations for capacitors, calculations for diodes and transistors. Transistors are like, dude, transistors are super interesting. That one little BJT transistor, bipolar junction transistor, there's a bunch of different interesting things that you can do with it. That one thing, apparently you can put it into like a couple of different modes where it behaves in different ways. It's pretty interesting once you dive into the subject. Now, once you get into transistors, you'll notice that some of the example circuits that are being presented, they tend to use multiple voltage sources or multiple power sources. They'll use like a lower power source uh, for activating the transistor because that goes to the base, and then they'll use a higher power source for whatever they're trying to do. What was I saying? Yeah. So the idea with a transistor, one of the multiple uses of a transistor is that you can use it as a switch. So the the idea is usually if you have like a physical switch that connects two wires together, that switch, it's either going to be like an on off switch or a button or something like that. So when it's on, it closes the circuit, meaning it's the same as if those two wires were touching together, right? The circuit is closed, and then current can flow through it, and so you can, for example, light up an LED or something like that. And then if you switch the switch off or turn the switch off, that opens the circuit, which is the same as if the wire is disconnected. Now, this is with a physical switch, right? What if you wanted to do this electronically? So you wanted to control this opening and closing of the circuit, but electronically. That's where transistors can be useful. Words. Transistors have a couple of other use cases as well, because as I mentioned, they have like a bunch of different modes. They behave in different ways when you set them up in different ways, which we're also going to be diving into later once I do get into the topic of transistors. I've looked into it a little bit to a certain extent. I've used it as well. Um, I for example, it was mainly for like setting up example circuits. I think I had created an OR gate with it or an AND gate. I think it was an OR gate. I don't remember. Wait, where was I going with this? What was I saying? Yeah, so I want to do analog electronics research. Oh yeah, I was talking about like the complex stuff, the stuff that I tend to get stuck with. I want to do research on those things, and then of course I also want to do research on the more basic things which I never really got into too much, stuff like capacitors and diodes and transistors. I've gotten into transistors, but I didn't I didn't really get as deep into it as I wanted. Another reason I didn't go too deep into transistors is because a bunch of the different circuits they had um, they had multiple power sources. So earlier I was talking about some of the more complex topics, some of the more uh, complex analog electronics related topics that I wanted to do research on. This was one of them. How do you set up a circuit when you have multiple voltage sources or multiple just power sources in general? How do you set up how do you set up that kind of circuit? How do you know um, whether how do you make sure that you know the lower voltage part of the circuit is not getting higher voltage or higher current from the high voltage part of the circuit? How do you do calculations when you have multiple voltage sources in the circuit? Stuff like that. Um, yeah, yeah, I would definitely like to get into that. I also, dude, I've always wanted to set up um, 555 timer IC circuits, because dude, the 555 timer is and it's a very interesting IC. If you read up on this IC, there's tons of stuff that you can do with it. Like it is super interesting the way that this thing is set up. And it was like the first it was my introduction to ICs when I first started doing electronics research back when I didn't really know too much about like microcontrollers and stuff, and I was just mainly sticking to analog electronics. Um, it was my introduction to ICs, and once I did research on it, discovered like I discovered how people use discrete components to set up more complex logic, because you can look up 555 timer IC online and you're going to find like an entire schematic of how the thing is made. And it's interesting. The thing has like what 6 8 legs, I think, and or 6 8 pins, and each of those pins, aside from VCC and ground, the other 6 pins, the way that you connect them and how much voltage, how much current you give to each one of them, and at different times how you control the amount of voltage that's given to it, all of that can change its behavior, and all of that behavior is very very well described. It's very what's the word? it's it's very well documented. That's yeah. It's very very well documented. Hold on, let me open up the thing on Wikipedia to show you guys. This is a super super interesting thing to play around with if you're new to electronics. Of course, I mean at this point in time, I would recommend playing around with a microcontroller because there's so much more that you can do in terms of learning about circuits with a microcontroller than you would be able to with just like discrete component. Of course, uh, the microcontroller alone isn't enough. You do need discrete components, but you would be able to learn quite a lot using a microcontroller due to just the insane amount of examples that are available. As you start setting up those examples, setting up those circuits and understanding all the stuff revolving around it, because usually the examples include a mix of analog circuits and digital circuits. They're not limited to a specific type. Eventually it does go more towards digital stuff, but there's quite a bit of analog stuff as well in there. Okay, yeah. I was looking up 555 timer. Give me a second. I'm just opening this thing up. Okay. So this is the Wikipedia. Give me a second. Let me just do that. Okay, great. Cool. So this is the 555 timer IC. This little thing here is like the size of your like one third of your index finger. And there's a ton of stuff that you can do with this. There's a lot of fun projects that you can do with it. And I do wanna do a lot of different things with it once I have a good understanding of how to do calculations surrounding resistors, capacitors, and transistors. More specifically, capacitors. I never really got to the math side of capacitors. I know a fair bit about resistors, so that's fine. And then transistors, I definitely need to do more research on it. But here's what I was talking about. Like you can see the schematic here. Actually, there's different versions as well. There's this CMOS version and the bipolar version. I don't remember which one I have. And then there's this thing as well. Let me open this up here. Maybe it'll show up better. Yeah, so this gives you sort of a high level overview, I guess, of the 555 timer because it contains I think these are comparators. I'm not sure. I believe these are comparators, and then this might be a latch of some sort. Yeah, I think. Hold on, let me see what this says. Yeah, this is a internal block diagram. So these are like higher level components, which are made up of like, internally they can also be considered to be made up of discrete components. Though it's like, I mean, I'm saying they can be considered to be made up of discrete components, but that's not really how they're set up internally. But yeah, you can consider it that way. And then this, I think here they're trying to show us how you can build it, how you can build a 555 timer using uh, mainly transistors, resistors, and I think diodes. Yeah, I think so. But yeah, if this is what I was talking about. If you want a schematic of this thing to understand, how it's connected, you can have this, or you can just take a look at this specific thing. This, I feel like this block diagram will be more helpful in terms of understanding how the thing is working and why it's behaving the way it's behaving. But also, um, you have all of this extra information. So it mentions the 555 timer IC, or the 555 IC has the following operating modes: astable, monostable, bistable, and Schmidt trigger. And then it goes into details of how each mode works, what each mode does. Here's also a table which gives information about every single pin and how it behaves at different times when different things are happening. This is what I'm talking about. This is why I find like the 555 timer just incredibly interesting. So yeah, I wanna get into this as well. Um, where was I? Here. So ESP32 and analog electronics. And then what else was there? There was a bunch of like Unity stuff that I wanted to do, but like I'd been keeping it on hold until I would finish reading up on the Git stuff that I needed to read up on. Because the thing is, I wanna learn. Actually, you know what? I don't need to do that. I just realized that if I do want to start my project, what I could do is I could start the project on my I could start the project on the machine where I want to start the project, and whenever I'm ready to move this copy over to another machine, once I've set up the whole, Git server and all of that stuff, once I've set up the Git server and all, then when I need to move things around, I can just move the original project and um, set up like a clone on the other machine. Yeah, for some reason this idea didn't occur to me at the time. Anyways, yeah, so bunch of Unity projects that I want to work on as well. I wanted to start that game project. I think I'm gonna center the game project around feed forward neural networks, because currently I'm exploring feed forward neural networks. So I think I'll yeah, I think I'll center it around feed forward neural networks. Speaking of which, oh yeah, oh, you know what? Hold up. So I was about to say, speaking of which, let's go back to doing that. But then I remembered what else I was going to talk about today. So I was gonna talk about. So I was having a conversation with Gemini about. So like, okay, I know where I want to go in terms of like deep learning. After we are done with feed forward neural networks, I know that I want to explore convolutional neural networks and recurrent neural networks, and then transformer based neural networks. And then I want to go into specific tasks and which architectures I should be exploring in order to solve specific types of problems. Right? Then I can go, after learning these four basic architectures, then I can go into more complex things that use these architectures in different ways. However, though I have my own ideas for stuff that I want to explore. Mainly, my two ideas, if I'm being honest, my main two ideas were um, one, NLP, which goes more specifically going towards LLMs, and two, computer vision, which I have a bunch of like different ideas for that as well. And I wanted to do a little bit of work with audio as well, but like there's not too much. I don't want to say there's not too much interest. It's just that a lot of the ideas that I have, they not a lot of them revolve around audio. A lot of them do revolve around uh, images and video and LLMs, just NLP in general. So I kind of know what direction I want to go in, and I have my mind set on going in that direction. But I still wanted to ask Gemini that, hey, if you had to suggest something to me, if you had to suggest what direction to go in, or if you had to, like, given the knowledge that I have right now and given the stuff that I plan on doing, if I tell you the knowledge that I have right now and the stuff that I plan on doing, what possible options could you list for me in terms of learning deep learning stuff? So here's exactly what I asked Gemini. I said, I've been learning deep learning. I'm still fairly new to it. So far, I've learned how to build, train, and test feed forward neural networks. I'm planning on learning about CNNs, RNNs, and transformer based neural networks next. But I'm well aware that there's lots to explore in terms of architectures, and what I go with will depend on what kinds of tasks I want to tackle. But I want to know what options I have, but I want to know what options I have available in terms of architecture, subjects, and tasks. Okay, there's an ad playing right now, so I'm going to take a hydration break, and I'll see you guys in 30 seconds. All right, welcome back. So, just to reiterate that last sentence, I said, but I want to know what options I have available in terms of architecture, subjects, and tasks. Okay, so Gemini replied with this. It's great that you're diving deeper into the exciting world of deep learning. You've got a solid foundation with feed-forward neural networks, and you plan to explore CNNs, RNNs, and transformers in an excellent next step. You're right. The best architecture often depends on the task. Here's a breakdown of common deep learning architectures, the subjects they address, and the tasks they're designed to tackle. So first of all, it mentioned I'm gonna just sort of write bullet points here. So first, it mentioned CNNs. Okay, it said that the core idea is inspired by the visual cortex. Okay, the core idea is inspired by the visual cortex. CNNs are particularly adept at processing data with a grid-like topology, such as images, videos, and even some types of sequential data. They use convolutional layers to automatically learn spatial hierarchies of features. Okay. Key features, convolutional. Okay, this is explaining the architecture. Now, the subjects that convolutional neural networks would tackle are, or the subjects that convolutional neural networks would probably come up in, I guess that's what I should say, are computer vision, image processing. You know what? Let's write this down. So we have CV, image processing, video anal video analysis, and some NLP. Okay. What tasks it can? Oh, you know what? Let's do this. Subjects. And then under that, we have this. Now, what tasks it can solve or tackle? Image classification, then object detection, image segmentation, facial recognition, um, medical image analysis, and autonomous uh, autonomous. Did I spell that right? Yeah, autonomous vehicles. So all of these are pretty exciting, right? We should explore all of these things. I just realized something. The way that this has been presented, hold on, hold on. I love the way you've presented the various architectures. Wait, architectures along with their uh, subjects and tasks. Would you mind doing the exact same for feed forward neural networks? Real quick, because I just got this idea as I was reading this thing. What just happened? Okay, subjects. Right. So this is giving some ideas of stuff that we could do, possible things that we could do with feed forward neural networks as well. So this is going to be for later. This is something to explore later. The subjects are supervised learning, primarily used for supervised learning tasks where there's a clear input output mapping. Okay, okay. I should keep this in mind for when I'm trying to set up a bot that responds to specific commands. Yeah, yeah. I should do something like that. What else? Pattern recognition. That's interesting. Well, you know what? In a way, I guess, because like our classification task, technically it's pattern recognition. In a way, it's pattern recognition, right? It recognizes patterns of data in the image, and based on that, it classifies the image as, XYZ. Okay, then functional approximation. Learn complex mathematical functions. This is interesting. I need to explore this further to see what exactly this means, what exactly is going on here, and what can we use this for. What else? What else? Then we have basic data analysis, general purpose modeling of tabular or unstructured data. Okay, interesting. So, what tasks does a feed forward neural network tackle? And this is interesting because so far, the only two suggestions that I'd gotten for feed forward neural networks was classification and regression. I hadn't really gotten the other stuff. So, okay. Um, classification. Okay, we can write it this way: binary classification, multi-class classification, um, regression, tabular data analysis. I need to explore this. I need to explore this. Yeah, tabular data analysis, predicting outcomes based on structured data found in spreadsheets or databases. Example, customer churn prediction, credit scoring, etc. All right. Then we have, wait, hold up. This was supposed to come under something. This was supposed to come under tasks, I believe. Yeah. Tabular data analysis. Where was I? Recommendation systems. Recommendation systems. Then simple image recognition. And simple NLP. Oh, there's also game AI. We should test this out at some point. We should definitely test this out at some point. Learning simple policies for game playing. Okay, cool. So, we've done what? Feed-forward neural networks, convolutional neural networks. Now, let's take a look at recurrent neural networks. Oh, actually, I just noticed that it also listed a couple of others in addition to what I had asked it for. There's another section called Other Important Architectures and Concepts. There's autoencoders. There's generative adversarial networks, GANs. There's reinforcement learning. There's graph neural networks, residual neural net, residual net, residual networks. Why was that so hard to say? Why was that so hard to say? Residual networks or ResNets, and that's it for now. Okay, so we're gonna list out all of these because this is interesting. This is very interesting. Obviously, I'm not gonna like type out the entire Gemini explanation for all of these things. So far, I'm just listing these out, but I'm gonna keep this list in mind because it's gonna be really helpful for when I'm trying to come up with ideas for things to do using specific neural network architectures. Okay, so RNNs. The core idea, it's designed to process sequential data by maintaining an internal memory that captures information from previous steps in the sequence. This makes them suitable for tasks where context and order are important. Key features, recurrent connections, and hidden state memory. All right. Common variants are long-term, short-term memory. Okay, that's a kind of RNN. Then gated recurrent unit, which is also apparently a kind of RNN. All right, I guess we'll explore that once we get into RNNs. Subjects, yes. So the subjects that RNNs tackle are NLP, speech recognition. So we could probably uh, hold on, did I spell that right? Recognition. Yeah. So we could probably look into some audio related stuff as well. And then time series analysis, financial data, sensor readings, etc. Interesting. Okay. Then tasks. The tasks that RNNs um, tackle. I'm not sure with the word task. I'm never sure what word to use. Tasks that accomplish. Tasks that RNNs try to accomplish or complete. what's the right word to use there? Because it's not a problem. I mean, technically, it's a problem that we are trying to solve, but we don't say solve for task. Usually, with tasks, it's like completing a task or accomplishing a task. Okay, anyways, tasks. There's a couple of them. There's machine translation, translating text from one language to another. Okay, speech recognition, text generation, sentiment analysis, uh, time series forecasting, and music generation. Okay, great, awesome. Now we move on to something a lot more exciting, which is transformer neural networks or transformer networks. The core idea is that it's introduced as a powerful alternative to RNNs for sequence to sequence tasks, relying heavily on a self attention mechanism to weigh the importance of different parts of the input sequence. They can process sequences in parallel, making them highly efficient for long sequences. Okay, key features, self-attention, positional encoding, encoder-decoder structure. Okay, then let's look into the subjects. Specifically, what's listed here in terms of subjects, hold on, transformer, uh, let's just say transformers, subjects. The only two things listed here are NLP and computer vision. So for NLP, it says this is the dominant architecture in modern NLP, and for computer vision, it says um, it's increasingly being used for computer vision. So something called vision transformers and other variants are showing strong performance in image tasks. Now, speaking of tasks, let's see what tasks transformer networks can solve, can do, can accomplish. There it is again. Okay. Can accomplish. There's machine translation. There's text summarization. There's question answering. Okay, so a bunch of this is NLP related. There's text generation, sentiment analysis, code generation, image generation, and image classification slash object detection. Hold on. Object detection. You know what? While we are doing the, actually, no, there's more architectures down here, right? Okay. So another um, important architecture slash concept is autoencoders. The core idea with autoencoders is um, it uses unsupervised learning models, or these are unsupervised learning models that aim to reconstruct their input. They consist of an encoder that compresses the input into a lower dimensional latent space representation and a decoder that reconstructs the input from this representation. The tasks that autoencoders can accomplish, are dimensionality reduction, denoising, and anomaly detection, identifying outliers by their inability to be well reconstructed. Anomaly. Did I? Wait. Anomaly. Is that right? Yeah, okay. Anomaly detection. Then we have generative adversarial networks. Hold on. Tasks. There. Right. Generative. Did I say general? I don't remember if I said general. Anyways, generative adversarial neural networks. No, fuck me. Generative adversarial networks. I'm just fucking up this entire name. Right. Generative adversarial networks. Or GANs. I'm just gonna say fucking GANs, dude. So the core idea behind GANs is that it consists of two neural networks, a generator and a discriminator, that compete in a zero-sum game. The generator tries to create realistic synthetic data, while the discriminator tries to distinguish between real and fake data. That's interesting. That'll be an interesting subject to explore. Yeah, I feel like that'll be an interesting subject to explore. Okay, so the tasks that it can accomplish are, yeah, accomplish. Fine. I'm sticking with that. The tasks that it can accomplish are image generation, then image to image translation. What is that? What does that entail exactly? Converting images from one domain to another. Example, turning sketches into photos. Oh, that's interesting. Okay. Image to image translation, and then data augmentation, generating synthetic data to expand training datasets. All right. Next, we have reinforcement learning, or no, reinforcement learning with deep learning. Let me write it down exactly like that. Reinforcement learning, RL, with deep learning. Deep RL. Okay. So I've looked into reinforcement learning specifically, but I haven't looked into reinforcement learning with deep learning. So this should be an interesting thing. The core idea combines deep neural networks with reinforcement learning practices. An agent learns to make decisions by interacting with an environment and receiving rewards or penalties. Subjects. Um, you know what? I could have done it in this way, so it would have used less lines. The entire time I've been thinking about this, as I've been writing this for each section, I was thinking that I could have just done it in this way, and it would have been much shorter because as it is, I was doing like a comma separated thing. So it would have been much, much simpler. CV, okay. Okay, done. Great. So, what was I doing? Subjects. Subjects. Game playing, robotics, and control systems. Tasks. Training agents to play complex games. Example, AlphaGo, AlphaZero. Controlling robot. It's the same thing. Optimizing complex. Yeah, it's the same thing. It's just reiterating what was mentioned in. So then I might as well change subjects to tasks instead. Game playing, robotics, control systems. Right. Then, graph neural networks, the core idea, designed to operate on graph structured data data points represented as nodes and their relationships as edges. They learn by aggregating information from neighboring nodes. Okay. Graph neural networks, GNNs. Okay. Subjects. The subjects are social networks, molecular, hold on, molecular structures, recommender systems. Okay, tasks, node classification, link prediction, graph classification. Then we have residual networks, ResNets. The core idea, while not a standalone architecture type in the same vein as CNNs or RNNs, ResNets introduce skip connections or residual connections that allow the gradient to bypass one or more layers. This helps in training very deep networks by mitigating the vanishing gradient problem. Usage often integrated into CNNs for computer vision tasks. Okay, let's just write often used in CNNs for CV tasks. Okay, right. Now I'm gonna ask one more thing. These are amazing. Would you mind talking about um, diffusion models? For example, or wait, diffusion model architectures. For example, stable diffusion using the same format. I really like this format. The way that it's been presented is great. Uh, you're de- you're delving into one of the most exciting and cutting edge areas of deep learning. Diffusion models, exemplified by stable diffusion, have truly revolutionized generative AI, particularly in image synthesis. They work quite differently from the discriminative models like most CNNs for classification or sequential models, RNNs, transformers for language you've studied. Here's an overview of diffusion models with a focus on how stable diffusion leverages this architecture. I wasn't aiming at stable diffusion specifically, so I hope, like, I was just trying to use stable diffusion as an example, but like I was trying to get an understanding of diffusion models in general. I hope it doesn't lean too heavy on stable diffusion and sticks to just diffusion. But let's see. Okay, so the core idea, diffusion models are a class of generative models that learn to reverse a gradual diffusion process. Okay, imagine an image being slowly corrupted by adding random noise over many steps until it becomes pure static. All right. A diffusion model is trained to learn the inverse of this process, to progressively denoise a given noisy input back into a clean, meaningful data sample like an image. This iterative denoising process allows them to generate highly realistic and diverse data. That's interesting. How are they doing that with um, text input, though? That would be something interesting to explore. Key features: forward diffusion process, reverse diffusion process, UNet as noise predictor, latent space, autoencoder, okay, conditioning, all right, sampling strategy. Okay, so there's a fair bit to go into with this. Right. Um, so what should I write with this? Diffusion model. Yeah, okay, diffusion models. So, subjects. The subjects are generative AI, computer vision. Okay, so generative AI, the core domain for diffusion models focusing on creating new realistic data. Computer vision, image and video generation, manipulation, and processing. Okay, um, where was I? Yeah, probability and stochastic processes, the underlying mathematical framework of how noise is added and removed. Then neural network architectures, specifically UNets, variational autoencoders. I think that's what VAE stands for, and transformers for conditioning. Unsupervised. Give me a second. Okay. Sorry about that. That was yeah, yeah. I had to step away for a bit. So, where were we? Yeah. So there was a bit of a list here in terms of subjects. It said probability and stochastic processes. Okay, probability and stochastic processes. Then it says neural network architectures, specifically UNets, VAEs, and transformers. That's okay. Hold on. Um, this is okay. This is interesting. So, this I just realized this is mentioning which neural network architectures are involved when creating diffusion models. Specifically, UNets, VAEs, and transformers. Then it says unsupervised and supervised learning. While often conditioned, the core denoising task can be seen as self supervised. Okay, we don't need to look into that. Okay, so tasks. Let's get into tasks. Text to image generation. Good. So it covers text to image generation. I'm guessing it's also going to explain how it works. The most prominent application, creating diverse and high quality images from textual descriptions. Oh, it didn't explain it. Okay. Image to image translation. Let's say IMG to IMG. Translation. Then in painting, filling in missing or masked regions of an image realistically. Then outpainting, extending an image beyond its original borders by generating new content. Okay. Then image super resolution. Okay. Yep. Isn't this upscaling basically? Enhancing the resolution and detail of low resolution images. Yeah, would this count as upscaling, or is that like a different process? Or, well, is that a different task? I think this is upscaling. Image super resolution. I'm not sure. Okay. Image editing. Modifying specific aspects of an image using text prompts or other controls. Example, add sunglasses, change the sky to sunset, etc. Then video generation, audio generation, 3D content generation. Holy shit. Uh, video gen, audio gen, 3D content gen, and then data augmentation and medical image analysis. Okay, so we have a ton of text here. Okay, I'm definitely going to note this down somewhere because I'm going to use this. I'm def we are 100% going to use this as we go through, each different architecture, as we learn to do various things with these architectures. We're gonna use this list to get some ideas. Yep, yep, definitely. Okay, now what else did I want to do? This was one of the things that I was thinking about doing. What else was there? Dude, okay, so I finished Detroit Become Human, and I enjoyed that game a lot. Like, dude, you have no idea. I'd been waiting to play that game even though I had shitty frames the entire time. I'd been waiting to play that game for a good couple of years. To be honest, okay, I didn't necessarily have I didn't so much want to play the game myself as much as I wanted to watch other people playing the game. For some reason, I really enjoyed watching other people playing the game, which I guess it kind of makes sense because the game itself is more like telling a story, right? So as you watch people making these different decisions and different things are happening, it's like watching a movie, essentially. And because your decisions can influence how the story progresses, so the movie, quote unquote, it tends to have like a different outcome. It can go in like different directions, and you get to appreciate the storytelling from many different angles. So I guess that's why it was fun to watch other people playing that game. And I didn't really feel the need to play the game myself until like much later when I was like, holy shit, I've watched so many people play this game. I never really experienced it myself. I should try experiencing it myself at some point. Um, Hold on. What is this? This says medical image analysis. Did I write that there? Yeah, I did. Okay. All right. Now, I I definitely want to set up the TTS thing. Oh, you know what? We could look into that. We could look into that. Yes, we could definitely look into that. Uh let's do a couple of things here. So, Python multi-threading versus multi-processing. Okay, and then I'm going to open up a separate thing here. Give me a second. Okay. Sorry about that. So I need to give me a second. Python multi-threading. Right. So there's thread-based parallelism, and then there's Python multi-processing. Great. Process-based parallelism, and that solves our problem. Great. The problem in this case was the fact that the Google search that I did previously, it was not showing me these two specific links. That being said, yeah, let's transition back. Okay, so there's a couple of Medium articles. We can open up these. There's a couple of Stack Overflow threads that we can look at. There's probably something on Reddit as well. Okay, just a minute. I don't know what Stack Overflow is about to do. Okay, all right. We are good. Let's just zoom out. Maybe zoom in a little bit. Okay, all right. Right. I'm trying to understand the advantages of multiprocessing over threading. I know that multiprocessing gets around the global interpreter lock, but what other advantages are there, and can threading not do the same? Okay. Here's an answer that does cover the GIL aspect. Can we close the other way around as per so and so? Okay, hold up. Here are some pros and cons I came up with. Multiprocessing. Pros, separate memory space. Well, okay, I kind of know this. So, okay, from what I understood, um, with global interpreter lock, what the gist of it that I understood was it it basically makes it so you cannot run, technically, you cannot run more than one thread at a time, or Python cannot run more than one thread at a time, which, like, I don't get how multi-threading helps then. Okay, I could ask another question here. Python, what is GIL? So somebody can then give a proper explanation. And okay, what is the global interpreter lock? Holy shit, this is a 15-year-old question. That is crazy. What is the point of multi-threading in Python if okay, yep, good question, good question. That's what I was looking for. Python GIL multi-threading. Multiprocessing, multi-threading, GIL, okay. Why is a Python IO bound task not blocked by the GIL? Okay, all right, cool. So let's start here. What is a global interpreter lock and why is it an issue? A lot of noise has been made around removing the GIL from Python, and I'd like to understand why that is so important. I've never written a compiler nor an interpreter myself, so don't be frugal with details. I'd probably need them to understand. Okay. Python's GIL is intended to serialize access to interpreter internals from different threads. On multi-core systems, it means that multiple threads can't effectively make use of multiple cores. If the GIL didn't lead to this problem, most people wouldn't care about GIL. It's only being raised as an issue because, wait, okay, hold up. It means that multiple threads can't effectively make use of multiple cores. Okay, yeah. It's only being raised as an issue because because of the increasing prevalence of multi-core systems. If you want to understand in detail, you can view this video or look at this set of slides. Okay. Um, it might be too much information, but then you did ask for details. Note that Python's GIL is only really an issue for CPython, the reference implementation, JPython or Jython, and IronPython don't have a GIL. As a Python developer, you don't generally come across the GIL unless you're writing a C extension. C extension writers need to release the GIL when their extensions do blocking I/O, so that other threads in Python, other th words, other threads in the Python process. What the fuck was that? Get a chance to run. Okay, this answer is 15 years old. Um, So I'm not entirely sure how accurate the answer, how accurate this statement is. As a Python developer, you don't generally come across the GIL unless you're writing a C extension. I'm not entirely sure how accurate that statement still is, considering like the crazy amount of work that we are doing with Python now. Because like, you know, now 15 years later, there's been a lot of development and there's a lot of libraries and there's a fair bit of um, a fair bit of demand for multi-threading in one way or another. So, okay. All right, let's first understand what the Python GIL provides. Any operation slash instruction is executed in the interpreter. GIL ensures that interpreter is held by a single thread at a particular instant of time. And your Python program with multiple threads works in a single interpreter. At any particular instant of time, the interpreter is held by a single thread. It means that only one thread, which is holding the interpreter, is running at any instant of time. Okay, now why is this an issue? Your machine could be having multiple cores slash processors, and multiple cores allow multiple threads to execute simultaneously. Example, multiple threads could execute at any particular instant of time. But since the interpreter is held by a single thread, other threads are not doing anything, even though they have access to a core. So you are not getting any advantage provided by multiple cores because at any instant, only a single core, which is a core being used by the thread currently holding the interpreter, is being used. So your program will take as long as it takes to execute as if it were a single threaded program. However, potentially blocking or long running operations such as I/O, image processing, and NumPy number crunching happen outside the GIL, taken from here. So for such operations, a multi-threaded operation will still be faster than a single-threaded operation, despite the presence of GIL. So GIL is not always a bottleneck. Okay, all right, cool. What's the point of multi-threading in Python if the GIL exists? All right. In some cases, any application may not utilize even one core fully, and using threads or processes may help to do that. Wait, run that back. In some cases, an application may not utilize even one core fully, and using threads or processes may help to do that. But The issue with threads, which is like why we are talking about Gil right now, is that you can only use one thread at a time, even if you set up your program for multi-threading. So like I'm trying to understand exactly how multi-threading is helping in this situation if the program can still only use one thread and the other thread is technically not doing anything, even though it's a multi-threaded program. Okay, think of a typical web application. It receives requests from clients, does some queries to the database, and returns data back to the client. Given that IO operation, oh, I missed the ad timer, so there's going to be an ad playing in, I guess, a couple of seconds. Given that IO operation is order of magnitude slower than CPU operation, most of the time such an application is waiting for IO to complete. First, it waits to read the request from the socket. Wait, would network or well receiving stuff through a socket, would that count as an IO operation? Because if it does, then I need to take that in mind. I need to keep that in mind and take that into account. Uh, First, it waits to read the request from the socket. Then it waits till the request to the database is okay. So it's being counted as an IO operation. Okay. Then it waits. No, because oh, okay, yeah, yeah, yeah. All right. There is the ad. So there's an ad playing right now. I'm going to take a hydration break and I'll see you guys in 30 seconds. Okay, welcome back. Right, where were we? Then it waits till the request to the database is written into the socket. Wait, then it waits till the request to the database is written into the socket opened to the DB. Then it waits for response from the database and then for response to be written to the client socket. Waiting for IO to complete may take 90% or more of the time the request is processed. When single-threaded application is waiting on IO, it's just not using the core, and the core is available for execution. So such an application has room for other threads to execute even on a single core. Such an application has room for other threads to execute even on a single core. In this case, when one thread waits for IO to complete, it releases GIL and another thread can continue execution. Okay. Now, here's what I'm thinking, right? Wouldn't the program get blocked if the model hasn't finished executing? Like, let's say I use multi-threading, not, give me a second. Okay, sorry about that. So, like I was saying, now let's imagine this, right? So the idea is that we receive, so it's an IO bound task, right? Receiving the text. because we are definitely expecting to receive this input over the network. Just a minute. Okay. Um, where was I? Yeah. So now imagine. So the idea with the program is that we are constantly receiving we are constantly receiving data over WebSockets using WebSockets. So it's like a constant loop that's running. I think it might be running on a different thread. I'm not sure. Maybe it might be async. Though, okay, so this is the interesting thing. With IO bound operations, async works out great. Like if you're able to set up async for IO bound stuff, that's amazing. You don't necessarily need multi-threading then, because IO bound stuff is more like, it's not like number crunching. It's waiting for this, then waiting for that, and it's going to take however long it takes. But however long it takes, you don't want to be waiting for that long doing nothing, right? Give me a second. Yeah, you don't want to wait for that long doing nothing. So that's why you use async, or asynchronous programming, where you have this thing where you, how do I explain this? You set it to do the task. You set it to wait for the input, but then your thread is not blocked there. It kind of lets the thread continue executing, and it just puts that on pause. And as soon as that operation completes, your program then automatically jumps back there, and it continues from there, and then it jumps back to this location where, in the main thread where it was executing. So it's a pretty interesting concept. You're able to do this in like multiple languages. I have done this specifically in C sharp and in Python, and it's been super helpful in both situations. Um, so let's say the networking stuff, let's say receiving the input, which is going to be received using WebSockets. Let's say we do that asynchronously. So that's going to happen on the main thread, right? We want, and let's say we are running the model on a different thread, not a different process, a different thread, right? It's still the same process, but it's a different thread. So let's say we decide to run the model on a different thread, just so the main thread is not blocked. The issue is, technically we are still going to be blocked because the model is running. While the model is running, Gil is going to be keeping the interpreter connected to this thread, right? So it's not going to go back to the main thread until this operation is finished, again, because of Gil. And this isn't even an IO operation. This is quite literally using the CPU, or possibly using the GPU, but quite literally it's using the CPU. It's not an IO bound operation, right? So using multi-threading in this case would probably not work out that well. We should probably be using multi-processing instead, because multi-processing is going to make it so the entire thing is on uh, a different process. The entire, like the model itself is running on a different process. So if we come back to this, okay, so it's good to, well, okay, I was about to say that, oh, this is shared memory space, but like, no, it says separate memory space. So one challenge that we are probably going to have is um, synchronizing between the two. So we're going to have to find a way to go about doing that. Maybe we can send signals from one to another, or I can set flags between one. We're going to have to find a way to share data between the two. Actually, no, hold on. Do we need to find a way to share data between the two? Because like we are receiving on one, right? Does does it actually need to come back to this? Because if it's a separate process, I could probably get away with um, even playing the audio on that separate process itself, as opposed to coming back to this process. So we send the data from the main thread to that process, from the main process to that process. Let's call the other process the model process. So we can send the data from the main process to the model process, where the data will then go through the model, and the model will produce or output the audio clip or the audio data, and then we can just play the audio data through that. Though I don't think, no, actually, no, you know what, no, that's not a good idea, because what I want to be able to do is, for the sake of optimizing it, for the sake of making it as quick as possible, as fast as possible, because I know the processing is also going to take some time, right? So I don't want to waste any time. Um, I don't want to waste any time waiting for anything to complete. So as soon as the audio, because okay, it just occurred to me when I gave this idea, it occurred to me that the amount of time that it's going to take for that audio to play, the thread is not going to be processing anything. And if I set it to process something in that time, if I set it to run another input through the model, then the audio is not going to play, because then the thread is going to get blocked. So that's not a good idea. If we are keeping a separate thread for the model, let's just leave the model on that thread alone. Let's not do the audio stuff there. Let's do the audio stuff. So, okay, what we can do is we can run the model on a different process, get the output, and then send that output to the main process. So basically, it's going to be that we get the input on the main process, and then we send that input data to the model process. The model receives the input data, it processes it, it produces the output data, which is the audio data, and then we pass that audio data over to um, we send that audio data back to the main process where it gets played. I'm gonna have to find a way to make it so I'm gonna have to find a way to make it so this process is like continuously going on. So maybe there could be a queue on maybe there could be a queue on what do you call it? Maybe there could be a queue. How am I gonna send the audio data from how am I gonna send the audio data from one process to another? Is there like a simple way to send the data back? IPC is a little more complicated with more overhead. Communication model versus shared memory objects. Yeah, okay. Shared memory makes access to state from another context easier. Great option for IO bound applications. Yeah, dude, I'm not too sure about. Yeah, I'm not sure. It seems like a separate process is a much better idea than multi-threading, specifically because of Gil. Because Gil is going to kind of ruin the entire point of multi-threading in the first place, right? Um, if we really consider what's if we really consider like what's going on within our program, the model running is what's going to consume the most CPU time, right? So if we switch to that thread, then the interpreter is going to be locked with that thread, and it's not going to be doing anything on the main thread. So even if there's IO bound tasks on the main thread, that's going to be stuck. Okay, alternatively, something else that I could do is instead of using multi-threading or multiprocessing, I could set up the IO bound thing as async, and then each time we receive something, so we keep everything on the main thread, and each time we receive something, we add it to a queue, and we have this loop. We have like an infinite loop running as long as there's items, or well, yeah, we just have an infinite loop running. I'll have to set up a program loop, and each time it's going to check if there's something, to process, if there's something in the queue, and if the model is not currently running, then it's going to pass the data in, process the thing, and then once it gets the output, it will immediately play that. Now, I'm wondering if there's like, okay, what happens if I start playing the audio, right? Let's say it's a long sentence. What happens if I start playing the audio and then, wait. What happens if I start playing the audio and then it loops back, like the because the program is in a loop, right? What happens if the audio is currently playing and then it goes back to the loop? Is it gonna like go back? Like is the loop, is it gonna exit out of the loop if the audio is still playing, or is it gonna finish playing the audio and then exit out of the loop? Not exit, but like um, you know, run another iteration of the loop. I need to find that out, because if like this whole thing is only gonna work if I'm able to set up some kind of separate queue for the audio to play, or some kind of separate thing in which the audio is going to play. Oh, you know what we could do? We could move the audio to a different process. We could move the audio playing to a different process. So it could work like this: the audio gets received, but wait, no, we're going to be in that loop. We still have to send the data. No, that might get complicated. That might get complicated. Does playing audio count as a IO bound task? Okay, let me try asking this question to. What should I ask this question to? Give me a second. Okay, so I'm gonna ask this question to DeepSeek, labs.perplexity.ai. Okay, so let's ask this question. Okay, so I have a program idea in mind, and well, let's say I have a Python program idea in mind, and but I have some doubts. Oh, you know what? Okay, I could ask it in this way. Let's say I have a Python program. In this program, I'm running an infinite loop, and within the loop, I'm um, playing an audio file, or well, playing an audio clip using some audio data that I already have loaded. Will the loop go to the next iteration before the playing of the audio clip is completed, or will it be stuck there until, or will it be stuck in that iteration until the clip finishes, until the audio finishes playing? Is there some sort of queue that the OS has set up for um, holding the audio clips? Also, if I moved the playing of the audio clip over to a separate thread, would Gil be released and returned and return control to the main thread before the audio clip finishes playing? Does playing an audio clip count as an IO bound task? In a way, it does, doesn't it? Like output. Okay, okay. All right. Great. Wait, is it done? Now it's done. Okay, yeah. Okay, let's try to figure out the answers to these questions. The user has a Python program with an infinite loop where they play an audio clip each iteration. The main question is whether the loop will proceed to the next iteration before the audio clip finishes playing or wait until it's done? First, I need to recall how audio playback works in Python. If they're using a library like Pygame or PyAudio, those might have blocking functions. Oh, you know what? Yeah, some of them do actually give you non-blocking options as well. Yeah, I remember that now. I could probably make use of that, dude. Though, how would that work if the last time that we were in the main thread, we were in a different iteration? How's that going to work? Okay, okay. Oh, wait, no. The last time we were in the main thread, we were in a different iteration, but like then we played the thing, which took us to that different location. And then because it paused there, it brought us back to the main thread where the main thread continued executing. And then once that thing is finished executing, once the other thing is finished executing, the control jumps back there so we can finish whatever other stuff we have to do. And then it comes back to the main, well, not main thread. Have I been saying main thread? Not main thread necessarily, but like the main control function. Yeah, no, we should be fine, even if we are within a loop, because the moment it hits that IO blocking operation, it will, or that IO bound task, it'll return control back to, the calling function. Um, and then it'll continue executing. So we should be good if I can manage to make it async. So what I need to look into is async audio. Yes. So there's a couple. Oh, okay. Hold on, guys. Sorry for the abrupt